Hello. So last time we looked at negative and fractional indices. So in particular with fractional, we looked at how that converts to square roots and roots in general. And we're going to expand a little bit on that in this section. So here we're going to look at surds. And surds are essentially a type of square root where we have a number n that's been square rooted, but this number n is not a square number, okay? So remind you the square numbers are, so it cannot be not 1, 4, 9, 16, and so on. So numbers that square root to get a nice whole number, right? So root 1 is 1, root 4 is 2, root 3 is 9, and root 16 is 4, and so on. Now, every number not in the groups in between all these numbers, if you do root them, then they are irrational, which means that it's an infinite decimal. If you were to write it in a calculator or try and work it out, there'd be a decimal, which will just be going on forever. Okay, so in theory, you can't write the number down because it's just always ongoing. So, for example, then root 1, that's equal to 1. That's an integer, and 1 is a square number, so that is not a third. But then root 2 is a third because root 2, I mean, if you put that in calculator, you're not going to get a nice number. You'll get a decimal that'll be ongoing. Now, the calculator only give up the first 10 digits, but actually that number is ongoing. But it's just that the calculator only has a limited amount of room, and obviously, as I said, an infinite number that always goes on. So it won't be possible to calculate all the digits. So that is some decimal. We don't know what that is to the matter, but that means it is a third, and that's simply because 2 is not a square number. Because root 2, if you root it, and as I said, you don't get a whole number, so it's not in this list, right? In the same way, root 3 is also a third because 3 is not a square number. If you root 3, you don't get a nice number, so it's also a third. But then root 4 is 2, and we can see that there. Root 4 is here. So it is not a third. Okay, and we can keep going on, and hopefully you spot that essentially, as I've just said here, at the top here, that if we have a root of a number where n, what we're rooting, is not a square number, it has to be a third, because we cannot simplify it nicely to get a whole number. And what we'll get instead is it's just an ongoing infinite decimal, so it'd be an irrational number. Okay, then we can look at more properties of roots. So we looked at index laws and fractional indices last time, but when we're dealing with surds or roots in general, but with surds as well, whilst we cannot get actual a good nice number, we can simplify them. So these two laws in particular. First of all, if we times in hang on. No, so if we are timesing two thirds together, I kind of gave it away there. If we times the two thirds together, right, two square roots, then naturally you can bring them together as one, okay, in this way. So then, for example, and we'll look at some examples in a minute. But for example, root 6, we can say is root 2 times root 3. And hopefully you can spot 6 is just 2 times 3. Okay. And the other one is essentially when we have a division then. So if we have A over B, so A and B are obviously just numbers to the matter. We can split the root up to the top and the bottom separately. Okay. And those are the two essentially you need to be aware of. Um, okay. And that's all. That's essentially. So we're going to apply all this now. So let's have a look at some examples. So, as I said just earlier, like a minute ago, the good idea we want to simplify surds, even though they give us a nasty number if we just put it in a calculator or whatever. But we can simplify them to get smaller numbers, which should be a little easier to read. Okay. To interpret what the value is. For smaller numbers, we can visualize and we know what smaller numbers are compared to bigger ones. But anyway, let's have a look at this in practice. So part A, root 12. And so the whole idea is we're going to use the idea of square numbers, right? Because we know square numbers do give us a nice number. So, for example, root 4 is 2, root 1 is 1, root 9 is 3. So the whole idea is we're going to use these surd laws, these two surd laws I've just wrote down here, and square numbers, right, to simplify, to break down large surds into smaller ones. Okay, so route 12, well the whole sort of strategy with this is to think think of a product, all the factors are 12, or a number in the square root general. The factors are 12, for example, here. That's the square factors, okay? And 12, you should spot, is 4 times 3. That's one factorization to try. Remember, we talked about factorization a few sections ago as well. That's essentially a product of a number, right? So we can split a number up into the multiplication of factors. So that's factorization. So that's one way of writing 12. And why have I done that? Well, now I notice I have a product right here. This third law here. This third law is going to be key with these simplification questions. But I have a product under our two numbers times together under the root. But that means I can split them off. So we have root 4 times root 3. Now, what's the beauty of this? Well, root 4 we can evaluate, can't we? That gives us a nice number. We know root 4 is 2. So that'd be 2 times root 3. Root 3 we can't do anything more, and we can't not break it down any further. Um, because, well, 3 is a prime number. What that means is we can't find any more like factors of 3. Because the only factors 3 are 1 and 3, but that doesn't help us. So we have 2 times root 3. We can just simply bring that together as 2 lots of root 3. Not to be confused by, make sure you put the 2 big, okay? Not to be confused with putting the 2 here, which should be just the square root of 3. What we have is 2 times root 3, okay? Just a little, make sure of you write clearly there. But yeah, so that's the whole idea. The whole idea with this whole section then is to essentially use the the third law, the product, so we can split surds up, and we're going to try to factorize with the square factors, okay? Let's have a look at part B. We have root 20 over 2. We're going to simplify the third bit, right? So root 20, what goes into root 20? Right, we can have 10 and 2, or we have 5 and 4. Now, 10 and 2 aren't square numbers, that's not going to help. But 5 and 4, 5 times 4, well, 4 is a square number, so that will help. So you can say root 20 is 5 times 4, that's all over 2. And then we can say that's root 5 times root 4 over 2. And now the root 4, again, like with part A, we can go to 2 times root 5, right, over 2. And so actually what you then notice is the 2's cancel, okay? Because we having multiply 2 at the top, but then we divide, oh, that's 2, not an x. But then we divide it by 2, so it just simply goes to root 5, okay? And notice now we've got a fairly weird, I guess, awkward looking fraction with a third, and we've got a simple, smaller third at the end. That's a lot more easy to interpret. Because we know that root 4, for example, is 2, so root 5's got to be close to just over 2, right? Like 2.2, 2.3. So that's the whole idea of this. Even though, yes, you have a calculator, that will just do it for you, but that's the whole idea. Part C. Okay, part C is a bit more tricky. So 5 root 6 minus 2 root 24 plus root 294. Now, the key thing is when you're adding, it's that there's no laws we have with adding surds. The only rules we have are to do with multiplying and dividing. Nothing to do with addition. So when you're adding several surds, the only thing you can do is simplify all the surds separately, and then perhaps you get a common surd, which then you can add together. Let's have a look what that means. So let's have a look at the first one. 5 root 6. Can we simplify that anymore? Well, the factors of 6 are 6 and 1. or we have 2 and 3, none of which help us because none of them are square numbers. Okay, so we're going to leave 5 root 6 where it is. Then what about 2 root 24? Well, 2, let's leave it there. But what about root 24? Can we simplify that? Well, what the fact 24 and 1? Okay, that's not going to help us. 12 and 2? Not going to help us. We have the 3 go into it. 3, 3 and 8. Root 3, root 8. No, what about 4? Well, yeah, 4 and 6, right? 2 times 4, uh, 2 root 4 times 6. And why have I picked 4 times 6 over the other factors of 24? It's because 4 is a squared number, okay? So that'd be 2 lots of 4 times 6. Again, 6 times 4 is 24. Okay, but then that's going to go to root 4 times root 6. And root 4 then is 2, right? So we can simplify that to 2 times 2 root 6, but 2 times 2 is then 4, okay? So we're left with 4 root 6. Cool, so simplify the second bit. And then what about the last bit? Okay, well, 294. Well, what I wouldn't advise in this particular instance is just list all the factors. There'll be too many. What you instead do is, well, recognise what we're doing here. What have we done so far? Well, look at what we've got. We've got root sixes in both of them. When you're adding and subtracting, you can only add and subtract the same surd. Okay, it's exactly like if I said that x was root 6. It's exactly like collecting like terms with algebra. If we say x was root 6, for example, we would have 5x minus 4x. That is why we can say, but that's simply x, okay? So it's saying I have 5 lots of root 6 and then take away 4 lots of root 6. I just have a root 6 left. So the only thing I can do here is consider root 6s because that's the only surd that's the same. It's the only thing I can do here. So with that in mind, I'm collecting root 6s, so I'm going to need 6 to be a factor of 294. Okay, so I need 294 to be 6 times another factor. Well, how am I going to work that out? Well, I can just do 294 divided by 6. Okay, and this will make sure I get a root 6 as a third. Okay, so then all three numbers are in terms of root 6. So that means I can add and subtract because then they're kind of like terms, right? I can collect them all, like I did earlier. Okay, well, 6 times 294 divided by 6 then gets me 49. Okay, so that'd be the other factor. So 49 and 6 are the factors of 294 that I'm looking for. And that's great actually, because root 49 again is a square number because it roots to 7. So 294 then will go to root 6 times 49. Again, to reiterate, I specifically looked for a factor for 6 because all the other two surds already have root 6 in them. So that means that I can take and add them away if they're the same surd. Anyway, so then I have 6 times 49. Well, that splits up, again, using the third law, where I can split them up. So that'd be root 6 times root 49. Root 49 is 7, so that'd be times 7. So I'm simply left with 7 root 6. But now, all three of them are the same, so it kind of like collecting like terms. If I said x was root 6, right? Then I'd have 5x minus 4x plus 7x. And it's exactly like collecting like terms. So 5 lots of root 6 minus 4 lots of root 6, add another 7 lots of root 6. So that'd be 8x or 8 lots of root 6. Okay. 5 minus 4 is 1. 1 add 7 is 8. So that is the fully simplified form. Okay. And there we are. So that is the whole idea with adding surds. You cannot. There's no surd laws within adding. So the only thing you can do is to break down all the surds to make them the same. Okay, like we've done here, we made everything root 6. That then allows us to combine them together. Okay. Okay. So have a look at another example, and you can also deal with brackets involving surds and roots. And we can use that expansion knowledge that we looked at last time as well, earlier on in the section. So part A, we have root 2 lots of 5 minus root 3. Um, oh, and again, you expand it in the exact same way with a normal number. So I'm going to times root 2 by f inside the bracket. So root 2 times 5, well, that's just 5 root 2. Okay, I can't do anything more with that. But then I'm going to, then I'll take away. So then I'm going to do root 2 times by minus root 3. Well, that's going to be minus root 2 times root 3. But I know that I can combine them under one bracket, under one surd, right? Because I'm times the two surds together, that means I can bring the multiplication on as one. So instead of root 2 times root 3, I can just say root 2 times 3. But that'll be 5 root 2 take away at root 6. Um, and it says simplify. Now I could say perhaps root 6 was, again, go back to what we said, root 2, root 3. And then I could kind of collect like terms, but I have a root 3 doesn't simplify. So I think it is. So it'd be quite awkward to collect like terms if I have another root. So I think that's probably best to leave it in this form. I'd suspect. Um, but yeah, so that's essentially it. So we're using surd laws again to be able to expand brackets involving surds, and that'd be very helpful when we do rationalising denominators in the next section. Okay, part B, 2 minus root 3, 5 plus root 3. Again, I've double bracket, but I know how to expand that, just like the earlier section. I'm going to do the exact same method. So again, with the first number 2, I'm going to times by everything in the other bracket. So firstly, 2 times 5, that's 10. But then I have 2 times root 3, that's just going to be 2 root 3. Okay, I can't do anything more with that. And then I'm going to look at the next term, which is negative root 3. So that again, negative root 3, I'm going to times by everything in the other, all the terms in the other bracket. So minus root 3 times 5, again, that's just going to be minus 5 root 3. 5 lots of root 3, not much I can do there. But then minus root 3 times root 3, so we're going to have minus root 3 root 3, or times by root 3. Again, I can bring it under the bracket to say 3 times 3, but that'll be 9. And root 9 we should know is 3. So actually that gives us the whole number. And you can spot that here because root 3, that's simply times in the number by itself twice. So we have 3 squared, but obviously root 3 squared, they cancel because the square root and the square are opposites in a way. So that'll just be left with 3. But anyway, we get 3 there. Hopefully you can see that. Well, we can simplify it, can't we? Because we can first deal with the actual number, so the 10 and the minus 3. By 10 minus 3 is 7. And then I can collect almost the root 3 as their like terms, in a way. So I'm going to have 2 lots of root 3, take away 5 lots of root 3. That's going to be negative 3 lots of root 3. And I can't do anything more there. Obviously, root 3 is small as it is. I can't do anything more to break that down. So there we are. Cool. So that's essentially the idea with surds. So let's look at some more examples then. Have a look at some exercise examples. Okay, so let's have a look at this. So we are told to simplify root 75 minus root 12. Okay, so exactly what I talked about earlier in the other question. When we add and subtracting, we're not multiplying or anything. So we can't use any surd laws directly. So the only thing we can do is to simplify the surds by themselves, okay? And then see what we can do from there. So first of all, root 75. How can we simplify it? Well, what square numbers go into 75? Well, immediately I recognise 25 and 3, okay? And 25 is a square number because then that would be left with root 25, which is 5, right? 5 squared is 25. So I can say it's 5 times root 3. Well, that's just be 5 root 3, okay? Okay, that's root 75. Then what about root 12? Well, root 12, well, again, I recognise 4 and 3 go into 12. And why 4 and 3? Because 4 is a square number. So 4 is a square number factor of 12. So then I could say root 12 is root 4 times 3. I could split it up into 4 and 3. Well, then root 3, well, root 4 is 2. So I can say that's 2 lots of root 3. Okay. There we are. We can actually work with this now. We can simplify it because they're both in terms of root 3 now. So now I have 5 lots of root 3, take away 2 lots of root 3. That's 3 lots of root 3. Okay, and there we are. It said to put this answer in the form a root 3. If we compare, clearly a has to be the 3 outside. And there we are. So hopefully you recognise the idea, right? We're using we simplify each surd by themselves by breaking it down into factors, and we want the square factors, which will allow us to break down the surd. Okay, so 25, for example, and 4 here were the square numbers. So that allowed us to simplify and make the surd smaller. Okay. Cool. Let's have a look at this set. We are given that 4x to the 3 plus x to the 5 over 2, I believe, can be written in the form 4x to the a. So I'm going to write this down: 4x cubed add x to the 5 over 2 over root x. Can be written in the form 4x to the a plus x to the b. Okay, so hopefully you notice there's no fraction in the final answer. So that means we're going to need to kind of split up this fraction. Okay, that's a common strategy with this sort of thing before we simplify anything. So if we're going to split this fraction up, we're going to have 4x to the 3 over root x plus x to the 5 over 2 take away root x. Okay. But then what are we going to do? Well, hopefully you recognise we sort of have two x's dividing, so we can kind of take away powers, right? It's kind of looking at the third law that x to the a over x to the b is x to the a minus b. I can take away the powers. We're not completely in this form yet because this root x isn't a power. But think back to the last section. How can we write a square root as a power? We can use fractional indices, and root x or root of anything is a half. So we can say root x is x to the half. And now we have exactly powers, hopefully spots, so now we can take them away. Well, then for the first fraction bit, I have 4 over 4, that's it. And then we have x to the 3 over x to the half, so I'm going to do x to the 3, take away a half. And so then that should be 8 over 2. No, 5 over 2. 5 over 2. Yeah. 3 over 2 is 6 over 2. So then 6 minus 1 is 5 over 2. Okay, cool. And then for the next bit, then again, I'm going to do the exact same procedure. Well, I'll have x at 5 over 2, take away a half. Well, that'll be 4 over 2, so that'll be x. That'll go to 2. Okay, so x to the 5 over 2, take away a half, would be left with 2. Okay, well now that's it. Our answer is in this form because now we have 4x to the a, where a is the power. But clearly, again, if we compare, a here would be 5 over 2. So a here and a there. And b up here is the 2. Okay, so we're good. And I picked this question. This sort of style of like simplifying surds with not surds, fractions with surds and indices will be very important when you look at the later topics. This is a key skill that you'll need, particularly when you look at integration and differentiation and integration later on in the course. But it's good to be practicing this sort of thing now. Okay, and hopefully then if you ever stuck at differentiation or whatever, you can reflect and look back to this example to see how we approach it. Okay, that's those are the main exercises. I'm going to finish off on an exam question, and I think it's a fairly tricky one. But it's good we look at this to show how you really master the topic and show how you can apply this knowledge in exam and what level of algebra you need to work your way up to an exam level. Okay, so this is an exam question. Now, this wasn't the whole question, so it was a 4 marker in total. Now, this one is 2 marks. So you get 2 marks for this bit. But I think this was the most complicated step in the question. Um, and more importantly, like I said, it shows the level of algebra you need for an exam situation. So it's a good practice to really test your knowledge on what we've done so far. Okay, so we need to show that 2 plus root x minus x minus 4 times by a half x to the minus a half over 2 plus root x all squared simplifies really quite nicely to just this. So 1 over a root x, a is just a number. So it needs to kind of look like this, right? Okay, so how are we to get from this monstrosity to this? And again, this is where surds and fractional indices are going to help here. So firstly, I notice I have some brackets to expand and have a product to expand on the top here. So let's work with that then. So if I bring the fraction here, again, that's 2 plus root x. Then I'm going to have x minus 4 times by half x. So I'm going to do that here. X minus 4 of a half x minus a half. That is this bit here. So let's work with that, and then I can bring that in once I've worked it out. Okay, so essentially, expand the bracket. So I can firstly say I can do the first term, right? The x. So x times by the outside a half x minus a half. So this is saying x times a half x minus a half. That's going to need your indices skills. So remember, if we times into numbers with different powers, we add the powers. Well, you might think, what in the power is the x? Well, it's just 1, right? Because it's on its own. Remember that. But then we simply have 1 take, well, 1 add up minus the half. But so I have a half here that stands on the coefficient. So I have a half, the number, right? And then I have an x, 1 take away a half because I'm adding. So I have 1 add minus the half, so it's 1 minus the half because it times it, remember. So remember the index law, x to the a times x to the b is x to the a add b. Okay. Well, that goes to 1 minus the half is simply half. Okay. Okay, but that's the first bit. So that's half x minus a half. But then I'm gonna do this next term, right? The minus 4 here. So then minus 4 times half x to the minus a half. Well, there's not much we can do there. That's just going to be minus 4 um time. I'm going to bring that here actually. A half x to the half. Take away 4 times a half x to the minus a half. But this bit simplifies a little bit because 4 times a half is saying half of 4, right? Well, that's just 2. So I'm simply left with 2 x to the minus a half. Okay, cool. But then I noticed the other part of the question, everything else in terms of root x, in terms of surds or square roots. So I think it's a good idea that perhaps maybe now you could either do this 2 ways actually. You could rewrite everything else in terms of a fraction indice like this, or we could instead convert the fractional indices into a surd. Okay. Well, I know a half is simply root x, so it'd be half root x. So that's what the fractional power, a half, means. And then have take away 2, but then x to the minus a half. Remember, the negative is the reciprocal, so we need to create a fraction. So it's going to be 2 over x to the half. But then x to the half is again just root x. So that's what we're left with, okay? So we can plug that in, so we're left with, so this whole fraction, not fraction, this whole product, right, this bracket situation at the top, goes to this, okay? We just worked that out, we expanded it, that's what we've done. So then that's simply a half, minus a half, x to the half. But then remember, we have minus at the front, so minus 2 over root x here, that becomes a positive, right? Because minus 2 minuses make a positive. So we have plus 2 root over root x. Okay, then we have all over 2 plus root x all squared. Now I'm going to do this expansion as well. Shall we do it down here? So 2 plus root x squared. So again, that's reminiscent of the past example we did earlier of expanding the brackets. So squared, you need to remember that is just going to be 2 plus root x times by itself. So I have another bracket. Okay. Now this I can expand. So firstly, again, 2, I'm going to expand times by every term in the other bracket. So firstly, 2 times 2 is just 4. And then 2 times root x is just 2 root x. Then then I'm going to deal with the root x, the next term in the first bracket there. So then root x times 2 is just another 2 root x. And then root x times root x. Hopefully you recognise that's just going to be x, okay? Because we're going to be left with root x squared, and then the x squared and the square root cancel to just left with x, okay? But this I can simplify a little bit, because then I know, well, I'm going to have x as 4. I can't do anything there. But then I have 2 root x and another 2 root x. I can say then that's 4 root x. So the bottom bit actually goes down to, if I get rid of this, I've expanded it, and now I can say that's 4 plus x plus 4 root x. Okay. Okay, what do I do now? Because this needs to go down to this. Okay. Okay. Like the next thing I notice is actually I can't have an ugly fraction here. I have this 2 over root x business over here. And there's 2 ways you can look at that. Either you can rationalise it if you know how to. Preferably should have done it GCSE. But actually, in this situation, because we have a fraction in a fraction, to get rid of this, I think it's best to just times by root x over root x on the top, on the overall top numerator there and the overall denominator here, and you'll see it goes quite nicely. For times by root x over root x, bearing in mind with any fraction, you can times by something like this. You can times the top and bottom by the same number, because root x over root x will just go, this fraction here will just go to 1, wouldn't it? Because root x is the same number, the top and bottom. So I'm not doing anything bad there, because I've just essentially timed it by 1. But if you times by 1, you get the same number anyway, or the same fraction. So I've done nothing wrong here. But if I times then everything on the top by root x firstly, I'm going to have 2 root x, 2 times root x. Then I'm going to have root x times root x. Well, that's just going to be x again, right? Because I have root x squared, that'll go to x. Then I'm going to have minus a half root x. Well, again, I minus a half root x times root x is just going to be x again. Then I'm going to have plus 2 root x then, because remember, you times in the numerator, you're going to times by root x on the top over root x. The root x's will cancel, so I'm just be simply left with 2. Okay, and that is why doing this step is quite nice, because then there's no nasty fraction in a fraction, okay? That it completely eliminates it. So times by root x specifically are times by the denominator here to get rid of the whole fraction bit, okay? Because then the root x here will cancel the root x there, okay? Okay, so that's the denominator, but a numerator, but I have to do the same to the bottom number because I'm times it by root x on top and bottom of the big fraction here, right? So root x then times by the denominator there, well, 4 times root x is just 4 root x. Then I'm going to have plus x times root x. Well, not much I can do there. That's just be x root x. And then plus 4 root times root x times the root x. Well, root x times root x again is just x. So it'd be 4 root x. 4x. Okay. Well, I can simplify the top bit a little bit, can't I? Because then I notice I have x minus half x. I can just collect the same term. Well, x minus a half x, well, that's just going to be just a half x. So I have 1x, take away a half x. 1 minus a half is just a half. So actually, this bit will just go to a half x. Okay. And there we are. Okay. It's still probably not particularly clear how we can really break this fraction down to what we want. But let's have a look at the final answer, and that's a good exam tip to see what we need to end up with. I need a root x on the bottom, okay? Um, so I think then if it's telling me I need a root x on the bottom on the denominator, let's see what happens if we factor out a root x on the bottom. Because then ideally things should cancel, right? So I'm going to leave the top number as at the top part as it is, 2 root x plus a half x plus 2. Then I'm going to factor root x in. So I have root x and then 4 root x. Well, that's just going to be 4, right? And then I have an x there, x root x. If I factor root x, you're just left with x. And then we have 4x. Okay, how do we deal with this? Well, the 4 will stay where it is. I'll leave it there for now. Well, how do I factor out a root x from x? Well, this is probably where the index laws are going to help visualize what's going on here, because I know that x on its own is just power of 1, right? So if I want to factor out, and if I want to times it by x to a half, well, root, I gave it away. If I want to factor out root x, well, root x is just x to a half, right? Then what else? And then I need to times by another number to get to 1. So I need to add another half one, don't I? Because then a half times a half plus a half, sorry, is just 1. So actually what happens is I could say x is simply root x times root x, and that makes sense, doesn't it? Because then that's root x squared, and that'll just get us back to x, okay? But that's how we can split that up. We can get a root x from x. Might sound a bit complicated, but essentially then we can factor a root x from x to get another root x. Okay? And we have a 4. Remember here, 4 on front. So 4 root x. Hopefully you can see what I've done there, okay? Because then again you can check your answer. We have root x times root x. You just get back x, okay? And yeah, so really now that should really help us. Let's have a look. Let's compare what we have. We have 2 root x, have a half x and 2 on the top, and have 4 plus x plus 4 root x on the bottom. Okay, well, we actually should notice now they kind of resemble each other. They're the exact same sort of powers of x, right? I have a root x here and here. I have an x term here and here, and I have a number here and there. Right? It actually, if I might actually, I'm going to make this more clearer. So I have 2 root x plus a half x plus 2. I don't have much room here. Um, so I have 2 root x plus a half x plus 2 all over root x. And then I'm going to rearrange the bottom bracket in the same way. So I'm going to put the root x term first. So I'm going to have 4 root x. And then the x term, so just x, add x. And then add 4 in the end. Okay, hopefully it's very clear now that they kind of match, right? And actually, I notice if you stare at it, that actually the bottom fraction, the bottom not the bottom of the fraction, the product, the factor on the bottom, actually is just double the factor on the top part, right? I have 4 root x in here. I have 2 root x here, so I just doubled 2 root x to get to 4. A half x on the top, I have x, so again I doubled to get to x from a half x, and then 2. Well, I double 2 to get to 4. So actually, I can then factor out a 2 on the bottom. So I have 2 root x plus a half x plus 2 um, over 2 root x now. Oh. And then if I factor another 2 out, well, that's going to be 2 root x. Because then 2 times 2 is 4. And then I need a half x here. Because then a half times 2 will get us back to 1. So that just get back to x. So we have a half x here. And then I have a 4 at the end. Well, then to factor a 2 out, I need 2. Because then 2 times 2 gets us 4. Well, now, doesn't the top bit exactly match the bottom factor? That means we can cancel. the top and the bottom factor. So I'm left with 1 over 2 root x. And there we are. I think we've done it, right? We've now got this into the form 1 over a root x, a the number, where we just found that we have 2 root x. So clearly a has to be 2 there. You don't have to, by the way, you don't have to write down, unless it actually tells you to write it down. What the A or any, you know what I mean, what the A or the B or missing, you're not missing values, stuff like that. But I'm just writing it down clearly to show how exactly how our answer compares to the form that they want it in, and that we've done it right. There we are. Cool. So hopefully you kind of noticed what we've done there. We did some expanding, we did some indices, we did some work with thirds to split stuff up. Again, it ties everything again together quite nicely. It's quite a tricky question, I think, though, especially with only 2 marks. I think this was the hardest part of the question as well. Like I said, this was the other half of the question. Um, yeah, I think it's a really good example to show the level of algebra that you might be expected to get to in the paper. But obviously, if you're just starting the course, this is at the start of year 12, I wouldn't worry too much. You get used to the algebra as you go on. Uh, but yeah, that's it for this section. And yeah, I'll see you next time.